In this video, we're going to prove that the non-zero rational numbers have a rational multiplicative inverse. So again, remember that when we defined what an ordered field is, one of our axioms is that every non-zero element has a multiplicative inverse. And so proving that that's true in the rationals is one step along the way to proving that the rational numbers, as we've defined them, is an ordered field. Let's recall our definitions for the rational numbers. If m is an integer and n is a natural number, then we define the rational number m over n as the set of all fractions p over q that are equivalent to the fraction m over n. And we define q to be the set of all rational numbers. So using these definitions, we can say that the rational number m over n is equal to the rational number p over q if and only if mq is equal to np. Also recall that if A is a member of a field, then an element B of that field is a multiplicative inverse of A if and only if AB times BA is equal to 1, the multiplicative identity. So you might be wondering what the problem is here, right? I mean, if you have a rational number P over Q, can't we just use Q over P as the multiplicative inverse? After all, certainly P over Q times Q over P will be equal to 1. Well, almost, but not quite. Okay. The problem is that if P over Q is a rational number, we know that P is an integer and Q is a natural number. Okay. So our denominator has to be positive the way we've defined it. Okay. But maybe P is a negative integer, so maybe P is not a natural number. All right. It's not a hard problem to fix, but it's something we have to be careful about. Okay, and we'll do that as shown in the proof. So the lemma that we're going to prove is that if A is a rational number and not equal to 0, then A has a multiplicative inverse in the rational numbers. Okay, so assume that A is a rational number and assume that A is not equal to 0. Let's suppose that A can be represented as P over Q, where P is an integer and Q is a natural number. Well, first, since A is not equal to 0, we know that P over Q is not equal to 0 over 1. And so we know that P is not equal to P times 1. P is equal to P times 1, which is not equal to 0 times Q. And that's equal to 0, so P is not equal to 0. Okay, so the fact that P over Q is not 0 over 1 leads to the conclusion that P is not equal to 0, using our definition of fraction equality. And so by a previous result, since P is an integer that's not equal to 0, we know that the square of P is greater than 0. So P squared is greater than 0. Okay, so that's great. That means that P squared is a natural number. So we can use it as a denominator. So let's look at P times Q over P squared. Okay, P squared is a natural number. P times Q is a product of a natural number and an integer, so it's an integer. So PQ over P squared is a rational number. And if we do the product, A times PQ over P squared, we see that that's P over Q times PQ over P squared, which is P squared Q over P squared Q. And now, I'm sure you're thinking that we're going to cancel P squared Q and the top and the bottom and we get 1 over 1. Actually, what's happening is we're saying that P squared Q over P squared Q is equal to 1 over 1 according to our definition of fraction equality. That is, 1 times P squared Q is equal to 1 times P squared Q. We don't have to be so pedantic as to write that, but that's really what we're using. We're not doing cancellation, which is essentially the same thing, but not what we're doing. Okay, so that proves that there is a multiplicative inverse of A in the rational numbers, namely PQ over P squared. So that completes this proof and this video. Thanks for listening.